the live stream.
Okay.
Okay, now you can go ahead.
Okay, yeah. Hi, everyone. I'm Leighton Guo. I'm from East China Normal University. I'm glad to try this session today. I'm sorry, my camera doesn't work well, so you may not see me. So it's a pity. And welcome to this S2S22 webinar series. And co-sponsored by NSF, NCSU, AISU, and East China Normal University and UCHER University. And today we are glad to have Professor Naishuang from Ocean University of China, and he will talk about the geomorphological processes in the Yellow River to Delta continuum. And a forecast next week, next Wednesday, we are going to have Varia Gary from Woods Hole. He or she will talk about organic carbon cycle in the Ganges Delta complex. And for today, and I will take this chance to introduce Professor B a little bit. And he got his PhD about 13 years ago from Ocean University of China, and now he was a full professor in the College of Marine Geoscience, and his research is focused on sediment transport processes and geomorphology dynamics in the lower Yellow River and the Delta systems, and that is also something about his talk today. So I will. So next, let's welcome Professor B. Can you hear us, Professor B?
Yes, I can. So
okay,
I will
please,
share my screen.
Go ahead. Yeah, it's your time. Yeah.
So can you see my presentation?
Yeah,
Yes.
yeah, very clear. Yeah.
Okay. Thanks, Leighton, for the introduction. Thanks, Paul, for giving me this opportunity to present our recent work. My name is Naishuang B from Ocean University of China. Today, my talk is about the geomorphological response of the Yellow River to dam regulations from river channel to delta. Actually, this is a teamwork with my colleagues from the Ocean University of China and Yellow River Conservancy Commission, and also Xiamen University, Japan. So we all know the importance of the river because they connected land and oceans. They deliver as much as 19 billion tons of sediment to the sea every year. So since the 1950s, human activities such as the rapid construction of dams and reservoirs in river basin has a significant impact on water regulation and sediment flux of global rivers. So because this change in the sediment flux and the water discharge, so the river channel morphology also change because the river delivered sediment will interact with the sediment in the river bed as variations in water and sediment discharges. And the change of fluvial processes, especially the decrease in sediment fluxes, has shifted the tendency of delta evolution. So large river deltas like the Mississippi, Nile, and the Changjiang deltas have converted to a destruction phase because of the drastic reduction of sediment supply from rivers. And the Yellow River was the second largest river in terms of sediment loads, with a widely cited value of more than 1 billion tons of sediment discharging into the Bohai Sea. So it's a source-to-sink process has become a global concern. And in this webinar series, at least I think 6 talks focus on the Yellow River sediment source-to-sink processes on different time and spatial scales. So like other large rivers, the water and sediment discharges to the sea from the Yellow River has decreased dramatically due to climate change and extensive human activities, such as construction of large reservoirs. So this figure shows the interannual variation of water and sediment discharges to the sea. So the red line is the sediment load, the blue line is water discharge. So it shows that a stepwise decrease of the water and sediment discharges after the construction of dams. So the Xiaolangdi Dam was in operation in 1999, and it enhanced this decrease in sediment load because the reservoir already has intercepted around 4 billion tons of sediments. And this is occupied about 3.3 cubic kilometers, and this space will accounting for around 25% of the storage capacity of the Xiaolangdi. Not only intercepts the sediment, so the Xiaolangdi Reservoir also regulates the water and sediment discharges to the sea. So in order to reduce the deposition in downstream channel and the reservoirs, so and increase also the flood carrying capacity of downstream channel, the VRCC, I mean Yellow River Conservancy Commission, began to use large reservoirs, Wanjiazhai here and Sanmenxia and Xiaolangdi for the water and sediment regulation scheme in July 2002. So the water sediment regulation scheme has two phases. The first phase, Xiaolangdi release clean water and lower down the water level in the reservoir, and also to erode the sediment in the riverbed. So you can see this is in phase one is very clean water, but during the second phase, the flooding water released from the Wanjiazhai and the Sanmenxia erode the sediment that intercepted in the Xiaolangdi Reservoir, and also exported high concentrated sediment to lower reaches, normally in form of artificial hyperpycnal flow. So this photograph shows sediment released from the Xiaolangdi during the phase two. And actually, since 2002, the water sediment regulation discharge to the sea have been regulated by the Xiaolangdi, as indicated by impulsive signals instead of the previous natural seasonal rhythm. So this figure shows a natural condition. You will see clearly the high water discharge in blue line, and in flood season from July to October, and corresponding to a high suspended high precipitation in the middle reaches, and also high sediment yield from the Loess region. But during the water sediment regulation scheme, you will see a impulse of signal of the flood water. So and also the water sediment regulation scheme contributed around 28% and 54% of the total annual water discharge and the sediment load to the sea in average, normally within around 20 to 25 days. So it greatly modifies the natural hydrological cycles. So normally in natural conditions, around 80% of the sediment discharged to the sea in 6 days. However, after the water sediment regulation scheme, it decreased to 30 days. So the water sediment regulation scheme has been carried about for 20 years. So it is necessary to systematically assess the impact of the water sediment regulation scheme on the river channel evolutions. So our study just want to answer the question that how does the erosion and deposition in Lower Yellow River respond to reservoir regulation on different temporal and spatial scales? So before I go to my result, I firstly introduce briefly the Lower Yellow River. So the Lower Yellow River is from the Xiaolangdi to the Lijing Station. It's about 750 kilometers in length. The Yellow River usually divided into three distinct reaches. That is a braided reach, transitional reach, and a meandering reach, based on according to their geomorphological characteristics. So from the topography of the river channel from upper to lower reaches, you can clearly see that the Lower Yellow River has a very gentle slope compared with the upper and the middle reaches. So as a result, a serious situation occurred in the channel, resulting in a riverbed higher than the surrounding area by 5 to 8 meters. So we called it elevated river channel. Since there's no tributary joining in the mainstream, so the region of the water and sediment are mostly dominated by the regulation of reservoirs of Xiaolangdi and other large reservoirs. So the Lower Yellow River is a typical region to study the erosion deposition of river channel in response to the regulation of reservoirs. And so we use the cross river transect data to calculate the erosion and deposition in the Lower Yellow River reaches. So this data were measured by the VRCC in each pre-flood and post-flood seasons. So there are around 225 transects from the Xiaolangdi to Lijing stations. The distance between two transects ranges from 2 kilometers to 13 kilometers. So we calculate the erosion deposition volume use a cross-sectional method that based on the area of cross sections and the distance between sections. This is the formula. It's a very simple formula, but it's also the only method we can use. We also collect the data on the daily average runoff and sediment discharge, which were measured by the VRCC as well. So let's go to our result. So here we showed annual deposition amount in the Low Yellow River. So this is blue. The positive value indicates deposition, and the negative value indicates erosion. So on the interannual scales, the lower reaches of the Yellow River deposit around 150 million tons per year before the construction of the Xiaolangdi Dam. However, after the Xiaolangdi is shifted to erosion, and with an average value around 100 and more than 140 million tons per year. We also study, spatially speaking, so this is different reaches. This is the braided reaches, because there are no significant difference between the erosion and the deposition value between transitional and meandering reaches. So we combine these two reaches as one reach. So here is this actually the entire reach of the Low Yellow River has changed actually from the deposition to erosion after the operation of the Xiaolangdi Reservoir. Before this Xiaolangdi Reservoir, there is a significant negative. We also established the relationship between these two segments. So before, this is before the operation of the Xiaolangdi reservoir, actually you will find there is a significant negative correlation between the erosion and the deposition in the braided and the transitional and the meandering reaches. However, after the construction of the Xiaolangdi, this relationship changed to a positive correlation. Okay, before the, especially actually erosion and deposition in braided river reaches are the most significant. So if you look at this figure, this is before the construction of the Xiaolangdi, this is after the construction of the Xiaolangdi. So before the construction of the Xiaolangdi, the deposition amount in the braided reaches in green bar accounted for around 77% of the entire Yellow River. However, after the construction of Xiaolangdi, the erosion in braided reaches about twice that in the transitional and the meandering reaches. It accounting for around 69% of the annual erosion value. And also we, because of different lengths of different river segment, so we also calculated the deposition intensity. So it shows that the erosion deposition intensity in braided reaches is one order of magnitude higher than that in transitional and meandering reaches. So not only we calculate the erosion and the deposition value, we also examine the change in the transection shape. For example, the channel depths and also the channel width. So this figure shows the spatial temporal variation in channel depths in bountiful discharge period. So the dashed line indicates transitional to meandering reaches. The solid line indicates braided reaches. So you will see before the Xiaolangdi Dam, so the braided reaches, the channel width in braided reaches actually has no significant variation, but the depth, but the channel width decreased significantly. So this indicates that the braided reaches is characterized by lateral sedimentation. However, if you go to the meandering reaches, so it's mainly shows that the decrease in the depth of the this dash line the depth water depth of the river channel. This means the transitional and meandering reaches is dominated by vertical sedimentation. However, after the construction of the Xiaolangdi, the channel in the braided reaches is widening and deepening, but in meandering reach is mainly deepening.
Naishuang, excuse me. We cannot see your computer, the mouse point. Is possible you can?
Okay, I will change. Can you see?
Oh yes, now. Okay, good.
Okay. So, okay, on the seasonal scales, the temporal variation in flood season actually is similar with the interannual variations, like we just showed earlier. So, but you should note that the flood season erosion and deposition in flood season it's decreased in recent years. So for the braided reaches and also the transitional reaches is quite different. So braided reaches is similar with the whole the interior reaches, but for the transitional and meandering reaches, it's mainly dominated by the erosion in flood season. In dry season, continuous erosion occurred in the lower Yellow River, and also the braided reaches. So where the deposition is dominated in the transitional and the meandering reaches. So, but the value you will see is decreased at the same time. Okay, so we also established the correlation between the two river segments. Here in the flood season, you will see before the construction of the Xiaolangdi, the relationship is a negative correlation. However, it's changed to a positive correlation after the construction of the Xiaolangdi. But in the dry season, it doesn't significantly change the relationship between these braided and meandering reaches. So it's all negative correlations. And we also calculate the erosion and the deposition intensities, and also it's a seasonal variations. So in before the construction of the Xiaolangdi Reservoir, the braided ridge, the erosion and deposition patterns in dry season was reversed in flood season. So you can see clearly it's the reverse value. So after the construction of the Xiaolangdi, the entire Yellow River, lower Yellow River that in blue was in erosion, and without a significant spatial variability as before the construction of the Xiaolangdi. And the total eroded sediment in flood season contributing to around 67% of the annual erosion. So that means the flood season erosion is very important for the entire Yellow River, entire lower Yellow River. So what is the role of the reservoir regulations? Because Xiaolangdi Reservoir, due to its significant sediment blocking effect, and has resulting in a significant decrease in seasonal and interannual sediment discharge. This figure shows the Huangkou Station, just the closest to the Xiaolangdi Reservoir. So this is water discharge for the interannual variation. This is in flood season, and this is sediment discharge variation. So we clearly show it clearly shows these two stages. So this is for the dry season, and also we calculate the incoming sediment coefficient. That means suspended sediment concentration over the water discharge. So you can also see clearly the decrease in this incoming sediment coefficient. Actually, in natural flood period, were mainly caused, the natural floods were mainly caused by heavy rainfall in the basin, resulting in a synchronization of sediment peaks and flood peaks. So high sediment laden flows significantly reduce the erosion efficiency of floods, which may cause rapid deposition in flood season before the construction of the Xiaolangdi. However, after the water sediment regulation scheme, you will see the artificial flood peaks were created here, and it will last around 2 weeks. But the suspended sediment concentration is very low, so the suspended sediment concentration was significantly lower than the sediment carrying capacity during the flood peaks. So this is why there is a significant erosion in flood season after the construction of the Xiaolangdi. So this also can be proved by the erosion deposition amount after water sediment regulations scheme event. So this figure shows the erosion amount in transitional meandering reaches after the water sediment regulation scheme event in 2002 and 2004. So it shows that this is the white blue figure shows erosion amount during water sediment regulation scheme event. So this figure is much higher than the value in the flood season. That means water sediment regulation scheme is very important when erodes lower Yellow River reaches. So it's so important that can the reservoir regulation maintain the continuous erosion in the Yellow River channel? Because we found that in recent years, the lower Yellow River actually shifted from erosion to deposition during one water sediment regulation scheme event. So this is the interruption of water sediment regulation scheme because of the climate change. So this is the erosion and shifted to the deposition. And if we if we take a look at the erosion and the deposition in these two phases, that means the first phase and the second phase, you will find that the erosion in the phase 1 is weakened, but the deposition in phase 2 is significantly enhanced. So for phase 1, we calculate the erosion efficiency, which is the erosion amount over the water discharge. It represents the erosional capacity of per unit volume water. So you also see it's decreased significantly by over twofold. That indicates that the resistance of the downstream riverbed erosion has significantly increased. So if you take a look at this figure, this is a green size change of the riverbed sediment. Maybe you will find the answer. So this is a green size in 2000, and this is the other years. So we find the green size increased significantly. So the cause of the sediment in the riverbed will form obvious armor layer that protected the underlying sediment from erosion. For the another question that needs to be answered is why the deposition in phase 2 is significantly enhanced in recent years. We established the correlation between the deposition amount and also the water sediment regimes. It shows that the deposition in the lower river channel in phase 2 was highly correlated with sediment released from the Xiaolangdi. So this indicated that the increase in sediment released from the Xiaolangdi dominated the deposition in the lower Yellow River in phase 2. So how the erosion and the deposition in lower reaches affect the sediment load to the sea? We established this simple model to assess the sediment budget in the lower Yellow River. We have the value from the for the Xiaolangdi reservoir release sediment, and we also calculate the erosion value in lower Yellow River channel, and we know that the sediment loss due to the water diversion, and also we know how much sediment discharged to the sea, but we don't know how much sediment deposited in the floodplain. But assuming that all the sediment released in Xiaolangdi can be transported to the sea, then we calculate that the sediment erode from the lower Yellow River contribute at least 60% of the Yellow River sediment to the sea. So this eroded sediment becomes the dominant sediment source, replacing the Loess Plateau. So the eroded sediment from the channel is coarser than that from the Loess Plateau. So this is a grain size variation during one water sediment regulation scheme. So it's much coarser than the period before this water sediment regulation scheme. So as a result, the sediment, the grain size of the suspended sediment to the sea also increased by more than 50% from around 17 macros to 25 macros. So how this change in sediment loads to the sea affect on the evolution of the delta system? So we use two types of data. One is remote sensing data. We extracted the shoreline based on this 33 scene Landsat images to examine the evolution of the data plan during 1976 to 2013. And we also use the 23 years bathymetric data to quantify the erosion deposition volume in the subaqueous delta. So next, I will show the temporal variation in the subarea evolution in erosion and the deposition of subarea and subaqueous delta. So both evolution in delta plane and subaqueous delta during 1976 to 2013 passed through 4 stages. So it's 4 stages. Propagation or deposition in the early 2 stages. This is the land area of the delta plane, and this is cumulative deposition amount in subaqueous delta. So the propagation or deposition in the early 2 stages with different rate were witnessed here. So both the first 2 stages is propagation. Then the delta transformed to erosion after 1998, both in subarea and subaqueous delta. And then it shifted to deposition again after 2003. Okay, this is 2003. This is a temporal variation. And spatially, so this is a spatial variability of the evolution of subaqueous delta. So this is a first stage deposition belt very close to the shoreline. And during stage 2, the deposition extent enlarged. But in the deposition stage 3, only limited area in deposition. Majority of the subaqueous delta were in erosion. However, in stage 4, deposition extent enlarged again. So you can see clearly it's much larger than this one. So why is this temporal variation like it just shows in the presentation? So I think first of all is sediment load. So we established the land area and the sediment load, the relationship. So during these 4 stages, so it's evident that the correlation of sediment load with land area and the deposition volume varied from phase to phase. It should be noticed that there is actually, I think we take a look at the series 3 and the series 4, because it's if you look at the sediment load, the red bar here, actually these 2 stages, there's no significant difference in terms of sediment load. However, the real amounts shifted from erosion in stage 1 to deposition in stage 2. So indicating that the sediment load may not control this phenomenon. So with the operation of the water sediment regulation scheme since 2002, coarse sediment eroded from the lower reaches become an important sediment source. So the grain size increased by over 50%, and also the settling velocity of suspended sediment increased twice, was more than twice that prior to the water sediment regulation scheme. So increasing settling velocity will limit the spatial extent of sediment dispersal. We also noticed that the sediment dispersal pattern has shifted from the hyperpycnal flow to hypopycnal flow in the Yellow River Mouth area. So we did a numerical simulation to examine the impact of sediment dispersal pattern on the morphological evolution, and found that the hyperpycnal flow favored the sediment depositing in nearshore area. So this is a deposition thickness difference. So the right one is the positive value in the close to the River Mouth area, I mean in the nearshore area. So both the increase in settling velocity and the shift in a sediment dispersal pattern resulted in stepwise decrease in critical sediment load that maintains the stability of the Yellow River Delta. Consequently, the active delta lobe shifted from the rapid erosion to considerable progression after the water sediment regulation scheme. So we know that the Yellow River sediment not only deposited in the delta region, but also transported from the Bohai Sea to the Yellow Sea through the Bohai Strait, and has become a dominant sediment source for the muddy deposit in the Yellow Sea. So this diagram shows the muddy deposit in the Yellow Sea, illustrated by Professor Yang and Paul. So numerous studies have examined the Yellow River sediment budget in East China Seas. However, there's a large difference among previous studies due to considerable uncertainty in estimation of the sediment deposit in the of the Yellow River Delta. So the sediment budget actually itself varied with the change in the Yellow River sediment load and the morphological evolution of deltas, as illustrated in this blue line. So this is a annual accumulation rate of the subaqueous delta lobe. So it's varied significantly. So we use our data of erosion and deposition volume and in the Yellow River Delta to assess a new sediment budget of the Yellow River sediment in East China Seas. The results show that around 70% of the Yellow River sediment accumulated in subaqueous delta lobe, suggesting that only around 30% of the Yellow River sediment has deposited in the delta plain and transported to the Bohai Sea and the Yellow Sea. So this value, I think, is less than 60 million tons to the Yellow Sea. And not only change the erosion and deposition pattern of the delta lobe by the water sediment regulation scheme, also the sediment causing of the Yellow River Delta. We studied the spatial temporal variation of sediments of the Yellow River Delta based on the grain size analysis of surface sediment in 1992, 2000, and 2015. So this is the grain size difference between 1992 and 2015. So the blue the blue color indicates the grain size increase. That means that the sediment in this area is causing by around over 10 micros. Not only the surface grain size, also we collect 4 push cores of the Yellow River Delta. We also it also shows that the sediment has been caused. You see that this is the median grain size by over 25% after 2000, recorded by this sediment cause. So the increase in sediment grain size mainly because the insufficient sediment supply, and also with along with the increase in grain size of the Yellow River delivered sediment. And the increased grain size also caused a significant increase in critical bed shear stress. So this increase in critical bed shear stress indicating that the erosion resistance was enhanced. Okay, I will go to my conclusions. So I think I will stop here, and I'm happy to answer any questions. Okay, thank you.
Okay. Thank you, Professor B. Yeah. Very informative talk. Yeah. Any questions from the audience? Yeah, just unmute yourself and go ahead. Anyone? Okay, and yeah, I will take this chance to yeah, and I want to know, yeah, Professor B, do you have you looked at the bed profile change in the lower Yellow River in the past 30 years, other than the erosion and deposition volume? And yeah, particularly given the operation of the dam and the water and the sediment regulation schemes. Yeah.
Yeah,
whether
actually, we don't have this kind of data, but my colleague in VRCC, they conducted multi-beam survey in I think very close to the Huang Coast station, and they found that the bed forms changed significantly after water sediment regulation scheme. So there's a lot of sand waves and prograded and also be eroded. Yeah.
Yeah, I mean the large scale bed slope along the
oh, you mean the bed slope, right? Oh,
yeah,
sorry.
Bed slope.
The bed slope. Yeah, and now the bed slope I think is increased compared with I think like the 2000 because the erosion in the lower reaches
increase. Okay.
Yeah.
Yeah, but you show that there's more erosion in the downstream of in the reaches more close to the dam, right? If that's true, then the slope should be much smaller.
Oh, actually, the Bradley Ridge is has very large wise, and the decrease in depth, I think, is less than wise. So because we only calculate the volume, so it depends on the change in depth and also the wise, right?
Okay, yeah. It may depend on how do you define the depth, right? The maximum depth or the cross section average depth. Yeah. Okay. Yeah.
Yes.
That's cool. Yeah. Thank you. Yeah. Any questions? Yeah.
So Naishuang, very good talk, very interesting. So I have a question. You said in the phase 1, in the beginning, the low reach, the erosion was very high, but gradually, the efficiency is decreasing, right?
Yeah.
So, I mean, how about in the future? This is expected because in the beginning, if you release too much water, will be eroded of the river bed. but gradually that kind of, the effect reduce. But how about future? Will they continue regulate, the reservoir to release more water, or they will adjust based on what you observed?
Yeah, that's a good question. So it depends on how the Xiaolangdi operated the water and the sediment, because now actually the lower reaches is safe to facing this flood risk. However, because now I heard about that, the YRCC will change the operation mode of the Xiaolangdi reservoir. They want to release as much as possible release as much as possible of the sediment from the Xiaolangdi to extend the life of this reservoir. Yeah. So yeah.
That means the lower reach of Yellow River could receive more sediment, because you said this is correlated with how much released.
Yeah, this is only based on the data of during one water sediment regulation scheme event. However, after the water sediment regulation scheme, the Xiaolangdi closed the sediment release gate. They release the clean water can also erode the sediment that deposit in the river channel during phase 2. Yeah.
Okay.
Yeah. So it's a temporary thing of the Xiaolangdi release sediment. Yeah.
Yeah. Okay. Yeah. Very good. Very good.
Okay. Great. Any other questions or comments? Yeah. Yeah, I may ask another thing. Yeah, and you in slide 24, right? You mentioned that there's a change between hypo and hypopycnal currents. So I'm wondering why there's such kind of things happening in this case. What's the driving processes?
Yeah, I think it's because I think there are two reasons. One is a decrease in the sediment load to the sea of the Yellow River. So, but you will find the water discharge actually increased after the operation of Xiaolangdi. So that means the suspended sediment concentration decreased. So if you want to generate a hyperpycnal flow of the river mouths, you need at least 35 kilograms per liter, 35 grams per liter of suspended sediment in the water column. So this is one reason. Another one, I think, is an increase in the grain size of the suspended sediment, because I think fine grain sediments favored the generation of hyperpycnal flow. Yeah.
Okay. Yeah. So you have model result show here, and do you have also similar observations, such kind of change?
Oh, okay. Yeah. Actually, every year we will carry out a field survey of the river mouth area to observe this hyperpycnal flow. However, unfortunately, we only recorded hyperpycnal flow in 2010, when the suspended sediment concentration at leaching station is greater than 40 grams per liter. Yeah. So that means hyperpycnal flow, I think, is dominated the sediment dispersal pattern of the river mouth area.
Yeah, that's interesting. Yeah. Okay. Anyone else?
Okay.
Yeah. Okay. Yeah. If there's no other questions, I will close this session. Okay, yeah, thank you, Professor B. Yeah, and
Okay,
thank
thank you.
for this talk. Yeah.
Okay, bye.
Okay, thank you very
Yeah.
much. That's
Yeah,
great.
thank you for everyone. Yeah, thank you for joining us.